The session 2 of Fundamentals of Additive Manufacturing Technology. So today we will be discussing on stereolithography processes and the subsequent portions. And we'll also be discussing about how the slicing takes place.
So these slice files, they are specific to 3D printing and they represent the 3D model after it has been sliced into individual layers or horizontal planes like this as shown in the images. So this is relevant to 3D printing. It does not directly represent the intersection between horizontal planes and triangles. Okay, so here this has been sliced into individual layers to prepare it for 3D printing. But here in STL file, or as the full form abbreviation is stereolithography file format, is this is the format which is widely used to represent 3D models in a format suitable for 3D printing and also computer aided manufacturing. So STL files are composed of triangles which are usually planar, composed of triangles that approximate the total surface of the 3D model. So these horizontal planes intersect with the 3D model and those intersections are represented by the triangles in the STL file. So the correct option is STL file. So in short, the intersection between horizontal planes and triangles in 3D models is represented by STL files, and this format is the most commonly used format for 3D printing and manufacturing processes. Okay. So we'll proceed. I hope this is clear. We'll proceed with the next question. Okay. So this was the main confusion people usually have is between STL file and sliced file. So STL file is the intersection between horizontal planes and triangles, and sliced file is um, only specific to 3D printing. That is, we have some external softwares where we slice the file before 3D printing and make it ready for 3D printing. So in slicing, while we do the slicing, we uh, separate into individual layers, the horizontal planes, to prepare it for 3D printing. So after that, while slicing, there are some various we prepare the file so that it can be read by the 3D printers and the files can be printed. So slicing is only relevant to 3D printing. It does not directly represent the intersection between horizontal planes and triangles in general 3D models. Okay. So the next question, which one of the following represents a valid solid model? Well, this is a direct question from our lecture notes. Any option? Answers? Okay, so most are answering option C, one which has only one interpretation. Okay, so solid models are known to be complete, valid, and unambiguous representation of the objects. So valid solid model is one that does not have any dangling edges or faces, while complete solid is one which has only a single point in space to be classified relative to the object. So the correct option is option B, one that does not have dangling edges or faces. So I think I'll discuss further because since there's many wrong. So see, when we do the modeling, CAD modeling for AM, so we have three types of solid models. One is complete solid, valid solid, and unambiguous solid. So when that is unambiguous solid, it has only one representation. So the completeness and unambiguity of a solid model, they are represented by the geometry and the topology. And then there are various methods for representing a solid, which will be discussed further, like boundary representation, space decomposition, hybrid modeling, etc. But uh, if we are asked about what is a valid solid, it is when we have a solid which is complete, which does not have any extra edges or faces in its surrounding. Like this can be said to be as a valid solid model, as it does not have any edges or faces which are dangling. But suppose we take a circle and we have extra rectangle protruding for it. This will be, in this case, this won't be a valid solid model. But here, this is a valid solid model. So uh, this is the correct explanation for this question. And the first option, this represents the next question is additive manufacturing technology, whether is it dependent on object geometry, true or false? Any uh, please answer. Okay. So additive manufacturing technology, it is correct, the option is correct, it is not dependent on object geometry. So we'll understand it clearly why. So as we know, additive manufacturing, also known as 3D printing, it is a manufacturing technology that creates objects layer by layer by adding material rather than subtracting it. So this process involves converting digital 3D models into physical objects. Okay, so now we have various methods where it like we have layer by layer fabrication, supports and overhang, build orientation, printability, material flow and cooling. So these are some of the reasons where the additive technology is dependent on object geometry, and here the design considerations play a crucial role in achieving the final 3D printed object. But there are also some points where we'll understand that, yeah, hello, yes, any doubts? I think my voice is not coming in between. Okay, so here um, the correct option is it is dependent on object geometry. Now We have various reasons for this: layer by layer fabrication, supports and overhangs, build orientation, printability, material flow and cooling. So these are the reasons due to which object geometry is dependent, 3D printing, additive technology is dependent. Yes, yes, please. See, see here. See, the when we do the layer by layer fabrication, okay, the additive manufacturing, it builds the objects layer by layer. So following the digital model's geometry. So here the shape and the complexity of the object directly influence how it will be printed layer by layer. Yes. Okay, let's take some examples. Suppose you have some certain geometric features, okay, such as very thin walls or in some sharp angles or some intricate details. So how will you print accurately? If it is not, so so their technology, so yeah. See, I'll just let me please proceed. So suppose like you have um like as I said, you have this material flow and cooling, okay, or when you have some very intricate structures like thin walls or sharp angles, or you where some in some portions you have the orientation of the object. Also, like we have to select appropriate build orientation, which is also influenced by the object's geometry. Also, in some cases, with objects with complex geometry, where we have some overhangs or undercuts, these may require support structures. Okay, so this is again dependent on the object's geometry and also the shape and the complex of the object. So object geometry definitely, it plays a significant role in deciding how you proceed with the your additive manufacturing uh, process. Yes, that is correct. I agree. The question should be additive manufacturing process. It's not technology. Yeah. Thank you for pointing it out. Okay. So we'll move to the next question. So STL format follows which method of representing a solid? Boundary representation, feature-based modeling, space decomposition, hybrid modeling. Uh, these are the four methods which have been discussed. So out of these four methods, which method is followed for representing a solid? STL format follows which method for representing a solid? The correct option is boundary representation. Now, the surface of the 3D object is defined by its boundary, which is represented by a collection of triangular facets or polygons in some cases of STL files. So each, suppose if I say each triangular is defined by three vertices, points in 3D space, and the collection of these facets forms the surface of the solid. So these facets approximate the shape of the object surface and collectively represent its exterior surface. So STL file uses this boundary representation method as they define the surface of 3D models using the collection of triangular facets. Now the STL format is suitable for 3D printing and various other applications due to its simplicity and ease of use. However, it is also we can say that uh, these STL files do not they only represent the object's outer surface. They never represent the object's interior surface or features. They only capture the surface geometry. So, so that is why here the correct option is boundary representation. And about these feature-based modeling, space decomposition, hybrid modeling, these are also used to represent the object's interior features and structures in various other CAD systems. Okay, so someone answered boundary representation now. Okay, so moving to the next question. Okay, which of the following ASTM standards are associated with additive manufacturing? This is a multiple question, so please answer. The correct option is option A and option B, ASTM F42 and ASTM 52900. So ASTM F42 and ASTM 52900. ASTM 42 is a committee on additive manufacturing technologies. ASTM 5290 standard specification, manufacturing file format, AMF. So AMF is an XML-based open standard that provides a method to describe the geometry and color of objects for additive manufacturing. So it allows storing both geometry and material information in a single file so that it is efficient for 3D printing. While this ASTM42, it is a committee on additive manufacturing technology. It is responsible for developing standards related to additive manufacturing processes, materials and applications. Okay, and about this ASTM D3039, it is a standard test method for tensile properties of polymer matrix composite material. it is not directly associated with additive manufacturing but is focused on the testing of composite materials. While ASTM E2109, it is a standard test method for cantilever bending method, modulus and damping properties. So it is also not directly associated with additive manufacturing, rather it is specific to textile materials testing. So the correct options are ASTM F42 and 52900. So next question. Which of the prototyping is associated with additive manufacturing? Virtual and physical both, none of them both. Okay, so the correct option is it is only physical prototyping. See, in this context of the question, additive manufacturing, uh, it is a it is a technology where we create three-dimensional objects by adding material layer by layer, uh, which we based on a 3D model. So what is a virtual prototype? Virtual prototyping. So when it comes to prototyping, we have two types. Virtual or physical. Now, when there is a product is defined, then the concept design and evaluation, then design analysis, then prototype. So this first three phases, this comes under virtual. Okay. Now, when this prototype becomes a 3D CAD model, now this entire thing becomes rapid or physical prototyping. So physical prototyping is also known as rapid. So the correct option is physical. So this entire process, when it happens, this is rapid prototyping. But till here, it is only virtual. So also one small example we can give, like when it is virtual, can be sketch of, suppose if we take an example, sketch of a car. Also CAD model of a car will be virtual. This will be virtual. Then physical will be when we have a prototype of a car. And also when we have a final product, that will be physical. Again we have a graph here. We can portray here, it is like this will be the complete, this will be virtual, so this will be virtual, this will be physical. So this is the most accurate representation, and this is a approximate or very rough representation of what you want. this is a small explanation for that. The next question. Which of the following processes extrudes molten plastic through a nozzle? Yes. Fuse deposition modeling, it is the correct option. So here we have a thermoplastic filament. This is fed into a heated nozzle. The filament is fed into a heated nozzle, and this molten plastic is then extruded through a nozzle as a thread. This may be of different dias. Suppose we can take an example of 1.75 or 2.85, depends on the nozzle. This is extruded through the nozzle as a thread, and next the 3D printer's build platform moves in the Z direction, nozzles move in the X and Y direction to deposit the molten plastic layer by layer. Now after this, each new layer fuses or bonds with the previous one as it solidifies or cools, creating a solid object. So this process allows uses various types of thermoplastic material, and FDM is one of the most widely used um, processes for 3D printing, as it is one of the common, accessible, and due to its ease of use, it is widely used in day-to-day 3D printing additive manufacturing industries. Okay, I'll just complete this. So this is the entire process of FDM process. Okay, so moving on to the next question. Okay, the starting material of the stereolithography method is in the form of which? Solid, powder, liquid, wire, gas. So earlier in the previous question we discussed about FDM. So now we'll be discussing on stereolithography. So it's in the form of which material? Liquid, solid, powder, wire, or gas? Yes, the correct answer is liquid photopolymer resin. So correct answer is option C. So in SLA method, stereolithography, SLA method, the starting material is in the form of liquid photopolymer resin. Now, now here a reservoir contains a liquid photopolymer resin. Now we have a UV laser or light which focuses or on the liquid resin, solidifying it layer by layer according to the 3D model. So here these solidified layers are there stick to the build platform, and the platform moves up or down to create the 3D object by adding one layer at a time. So now here this process continues until the entire object is formed. The liquid photopolymer resin, which is used in stereolithography, is this is very typically UV light. So when exposed to UV light, the resin undergoes a process called photopolymerization, where it solidifies and hardens. So this allows the 3D printers to create, because of this technique, it allows the 3D printer to create high resolution and detailed objects with smooth surfaces. Uh, the liquid nature of this starting material in stereolithography enables it the precise layer by layer solidification process, making it one of the most accurate 3D printing technologies. Okay, so I'll just SLA method is one of the most accurate 3D printing technologies. Now, here the process is reservoir contains a liquid photopolymer resin. Now, a UV laser or selectively illuminates the 3D resin, liquid resin, solidifying it layer by layer according to the 3D model. Now, as like FDM, the layers, as you discussed, the process continues until the entire object is formed. Okay, so the next question: which format of STL file is more compact and can be used for a file containing higher number of triangles? So we have two formats of STL file: ASCII format and binary format. Yes, the correct option is binary format. Now ASCII format represents the data's the data representing the triangles of the 3D model is stored as text. In ASCII format, data representing the triangles is stored as text. Now here the data is stored in form of binary. Data is stored in binary form. Now this results in a compact file size. The binary format directly encodes the data using a binary representation, reducing the file size significantly compared to the ASCII format. While here each triangle is defined by multiple lines of text, which increases the file size. Multiple lines of text, which makes the file larger, which makes the file size larger. Now, due to the compact nature of the binary format, it is preferred for 3D models with higher number of triangles or complex geometries. The smaller file size not it reduces the storage requirements but also facilitates faster data transfer and processing, making it more suitable for use in additive manufacturing processes. So, binary format is the correct option. Now, the next question, how many triangles are required to complete the STL file for of the below geometry? So, this is the cube. This is 6 faces. So in this, how many triangles are required? Yes, 12 is the correct answer. So since it is 6 faces, each face can be represented by 2 triangles. So correct option is 12. So here we have been given okay. So here we have been given the out. So we have to show the basic normal data whether it is redundant or not. So Now, first we have to find out each of the vertices of the triangle. So here we have been given the vertices. Uh, this is the these are the vertices. From here, first we have to find out the x1, x2, x3, y1, y2, y3, z1, z2, z3. Now, you can solve this simultaneously with me. Now here it is 320, 320, x2, and this is also 320. y1 is 100, 0, 0. This is 0, 300, 0. Okay. Now A cross B vector is equal to cap k cap. Now x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x2, y3 minus y2, and z3 minus z2. Now after solving this, we will get 0 minus 100, 300. This will be 0, 0 minus 300. Now simplifying this, we will get now 30,000 I cap plus 0 j cap plus 0 k cap. Now we will find the magnitude of this. This will be 30,000. Now this A cross B by A, magnitude of this. Here we will get it. I cap, this will be 100. Now the now we will compare this with the facet normal. Here also it is 100. So upon checking the vertex, check with the facet normal, which is 100 as given in the question. So the information is redundant here. Yeah, hello. Yes. Okay. So here you have been given the vertices of a triangle. Okay. And it is written, asked in the question, show that the facet normal data is redundant. Okay. This is the facet normal data. Yes. So we have to prove that whether this data is redundant or not. So we are finding out the n cap. Not exactly. So here, wait, I'll explain this. Redundant means whether the data it is yeah, required or not. It is not useful anymore. Okay. Huh. Your question is correct. So this is a subjective type question where we have to prove and show whether these vertices which are given, that is to prove that this normal data which is given, that is redundant. So this is the process of proving that. It's not that logical question where you have to show your data is redundant or not. We have to elaborate and show whether these vertices which are given, whether that is redundant or not. So this is the methodology for that. Yeah, this is the proof of proof of this is the process where we can prove that whether this data, if it is given, basic normal is given, and their vertices are given, then how to prove that whether this basic normal data is redundant or not. Okay. Okay. Next question is we have to write the ASCII code for representing the cube of side having side 1 unit in STL format. Okay. So first for this we will draw a cube. Sorry. Okay. So here this is our 0, 0, 0. This is our origin. So now we will mark all the points. We'll provide the coordinates for all the points. Okay. Okay. Now this is 1, 0, 0. This will be 1, 1, 0. This will be 0, 1, 0. Now this will be 1, 0, 1. Now first here, so this is the cube of side unit having 1. Now suppose we will take this as a triangle. Okay. Now we will take this as a triangle. So for this triangle we already have all the vertices. Okay. So here, so if we have the outer loop, so I'll first write the vertex. It will be 0, 1, 0, 0, 1, 0 and 0, 0, 1. Okay, these are the vertex. This is the end loop. Now we'll shade this for better representation. So this, in this way you will be representing your cube of, this is the way you will be representing. Now for this particular, and here your basic normal will be -1, 0 and 0. So In this way, you will be represent the SQL ASCII code for representing the cube of site 1 unit in STL format. Now, the final is now one thing you need to see that for each time this is always the facet normal. When we represent, it is the unit vector in the direction of a facet normal. So the group of three vertices defining the triangle is uh, uh, between outer loop and the end loop. Okay, and these vertices of the triangle are listed in a counterclock manner by using the right hand rule. So which we can find direction to the facet normal. So in various questions in our lectures also we have seen the initially the this is the nomenclature. First line is the nomenclature, as first you have to do the nomenclature, then write the facet normal unit vector in the direction of the normal, then write the outer loop, then the three vertices, then the end loop, then finally this is the format for representing the ASCII code. Okay, so these were the questions for today. Okay, any doubts?